Hello everyone. This is Chi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Hello everyone. Welcome back to our Deep Learning course. Today we're continuing with Chapter 4, Basics of Convolutional Neural Networks 2. And our focus is entirely on Part 4.3, Convolution, the core operation of CNNs. Let's break down what convolution is, how it works, and how to implement it with TensorFlow. First, let's clarify what convolution is. Convolution is a special type of linear operation, and its main role in neural networks is to replace the usual matrix multiplication. It's more efficient for processing image data. Two key parameters define a convolution operation. First, convolution kernel size, like how big the feature detector is, for example, 3 multiplied by 3 or 2 multiplied by 2. Second, output feature depth. This is determined by the number of convolution kernels we use. More kernels mean more output features. The slide shows an example diagram. On the left is the input image, a pixel matrix. On the right is the output feature map. The small matrix moving over the input is the convolution kernel. Each position's calculation multiply corresponding elements. Then sum gives a value in the output. Before diving into calculations, let's confirm, the convolution kernel we keep mentioning is also called a filter. It's the small matrix that scans the input to extract features. The diagram on the slide labels this clearly. This kernel is what helps us find edges, textures, or other patterns in the image. First, let's learn about full convolution. Calculation process. The convolution kernel, K, moves across the input, X, in row major order, meaning we go left to right, top to bottom. At every position where the kernel and input overlap even a little, we multiply the corresponding elements and sum them up. Why full? Because we calculate a value anytime there's overlap. If the kernel goes beyond the input's edges, the parts outside the input are treated as zero. We call this zero padding. The slide has a detailed example. You can see how the 3 multiplied by 3 kernel slides over the input, multiplies elements like 3 multiplied by 5, minus 1 multiplied by 2, sums them, and gets values for the output feature map. Let's wrap up full convolution with its results in code. The output of full convolution, labeled full on the slide, is the set of all those summed values from the kernel's scans. TensorFlow implementation, we use TF, NN, conv2d. Let's quickly go over the parameters. Input, the input tensor, like the image data. Filter, the convolution kernel. Strides, the step size of the kernel, usually 1, strides, 1, the 1SR for batch and channel dimensions. Padding, set to control edge handling. For full convolution, we use specific padding, but we'll focus on other types next. The slide also lists keynotes, input tensor size, convolution kernel size, step size, and convolution type, same or valid. These all affect the output. Next is same convolution. This is the most commonly used type in CNNs. The key feature of same convolution, the input and output have the same dimension. For example, a 3 multiplied by 3 input stays 3 multiplied by 3 after convolution. How to do this? We add just enough zero padding around the input so that when the kernel slides, the output ends up the same size as the input. The slide also has a table about where it all begins, the starting position of the kernel, but the main takeaway is, same convolution keeps the feature map size consistent, which helps preserve spatial information as we go through layers. Let's look at the result and code for same convolution. The output, labeled same on the slide, has the same rows and columns as the input. You can compare it to the full convolution output to see the difference. TensorFlow code, the core line is conv equals tf, nn, conv2d, x, k, 1, 1, 1, 1, same. The same parameter tells TensorFlow to add padding automatically to keep the output size the same as the input. The slide shows a complete code example. we define the input tensor x and kernel k with TensorFlow constants, run the convolution, and print the result. This code is easy to replicate, try it yourself later. The third type is valid convolution. Unlike full or same, valid convolution only considers positions where the kernel completely covers the input, no overlap with edges, and no zero padding. If the kernel can't fit fully on the input, that position is skipped. Calculation process: for example, if you have a 3 multiplied by 3 input and a 2 multiplied by 2 kernel, the kernel can only slide to positions where it's fully inside the input, so the output will be smaller than the input. The slides diagram shows this. You can see the kernel only moves to positions where it doesn't go beyond the input's edges, and the sum values are calculated only for those positions. Let's finish valid convolution with its result and code. The output of valid convolution, also labeled same on the slide, note this is a typo. It should be kvalid, is smaller than the input, since we only use full kernel coverage. TensorFlow code: just change the padding parameter to valid. Conv equals tf. nn. Conv 2d x k 1 1 1 1 valid. This tells TensorFlow not to add any padding, only use positions where the kernel fits fully. This type is useful when you want to reduce the feature map size without pooling. Now, let's learn how to calculate the output size for same and valid convolution. This is crucial for designing CNN architectures. The slide has a table that compares the two types. First, let's define the terms. Input tensor size, R rows height multiplied by L columns width. Convolution kernel size, FR rows multiplied by FL columns. Step size, SR vertical step, how much the kernel moves up or down, multiplied by SL horizontal step, left or right. Then, same convolution output, rows equals ceil, R or SR, ceil means round up, columns equals ceil, L or SL, round up. This ensures output size matches input. Valid convolution output, rows equals floor, or minus FR, divided by, /SR, plus 1, floor means round down, columns equals floor, O minus FL, divided by, SL, plus 1. This is the size when only full coverage is used. You can use this table to plan how your feature maps shrink or stay the same through layers. Up to now, we've talked about single-channel convolution like grayscale images. But real images have 3 channels RGB, so we need multi-channel convolution. The diagram on the slide shows the structure. The input has multiple channels, and the convolution kernel also has the same number of channels. Each kernel channel convolves with a corresponding input channel. Let's start with basic multi-channel convolution, one kernel, multiple input channels. Convolution process: for each input channel, we convolve it with the corresponding channel of the kernel. For example, input red channel, kernel red channel, green green, blue blue. Then, we add up all the results from each channel to get a single output feature map. The slide has a detailed example. You can see calculations like 3 multiplied by 5 plus, minus 1, multiplied by 2 plus 9, multiplied by 1 plus. For each channel, then summing those to get values like 80 or 7. This way, the kernel can extract features from all colored channels at once. Here's the TensorFlow code for basic multi-channel convolution. First, we define the input tensor x with 2 channels shaped like 1, 3, 3, 2, and the kernel k with the same number of channels shaped like 2, 2, 2, 1. Then run conv equals tf. nn. Conv 2d x k 1 1 1 1 valid. The valid means no padding, and the output will be a single channel feature map since we used one kernel. The slide prints the result, which matches the manual calculation we saw earlier. Next, one input tensor, multiple convolution kernels. Convolution process: we use more than one kernel, for example, 3 kernels. For each kernel, we do basic multi-channel convolution, convolve each channel, sum to one feature map. Then, we stack all these feature maps in the depth direction. The number of output channels equals the number of kernels. The slide's diagram shows 3 kernels, each producing a feature map like 80, 41, 29 for the first kernel, 101, 32 for the second, then stacking them to get a 3-channel output. This lets us extract multiple types of features, for example, edges, corners from the same input. The TensorFlow code for this case is similar, we just make the kernel have more output channels. The kernel K shape becomes 2, 2, 2, 3, 2 multiplied by 2 size, 2 input channels, 3 output channels equals 3 kernels. Run conv equals tf. nn. conv2d x k 1, 1, 1, 1 valid. The output will be a tensor with 3 channels, 1 for each kernel. This is how CNNs get multi-channel feature maps in convolutional layers. Now, multiple input tensors, batches, and multiple kernels. Convolution process, we have a batch of input tensors, for example, 2 images, each with 2 channels and multiple kernels, for example, 3. For each input tensor in the batch, we do convolution with all 3 kernels as before, getting 3 output channels per input. The final output is a batch of multi-channel feature maps. The slide's diagram shows 2 input tensors, 3 kernels, and valid convolution. Each input produces 3 feature maps. So the output batch has 2 tensors multiplied by 3 channels. This is how we process batches of images in practice. For example, a batch of 32 images, each RGB, processed with 64 kernels. The TensorFlow code here just expands the input to include a batch dimension. The input X shape becomes 2, 3, 3, 2, 2 samples in the batch, 3 multiplied by 3 size, 2 channels. The kernel K is still 2, 2, 2, 3, 3 kernels. Run conv equals tf. nn. conv2d x k 1, 1, 1, 1 valid. The output shape will be 2, 2, 2, 3, 2 samples, 2 multiplied by 2 feature maps, 3 channels. This matches how we train CNNs on image batches. Another important type, depthwise separable convolution, convolution per channel, no summation. Unlike basic multi-channel convolution, which sums channel results, this type convolves each input channel with its own kernel channel but doesn't add them together. Each input channel gets its own output channel. Process, for a 2-channel input, we use a kernel with 2 channels. Each input channel kernel channel convolution gives 1 output channel. So 2 input channels, 2 output channels, no summation. The slide's example shows, input channel 1 gives outputs 28, 15. Channel 2 gives 52, -8. These stay separate, not added. This is more efficient, fewer calculations, and is used in models like MobileNet. For depthwise separable convolution, TensorFlow has a special function. Code, conv equals tf. nn. Depthwise underline, conv2, d, x, k, 1, 1, 1, 1, valid. The kernel K here is shaped for per channel convolution, for example, 2, 2, 2, 3, 2 multiplied by 2 size, 2 input channels, 3 kernel sets per channel. The output will have input channels multiplied by kernel sets, channels. This is how depthwise convolution reduces computation while keeping features. For depthwise separable convolution, TensorFlow has a special function. Code, conv equals tf. nn. Depthwise underline, conv2, d, x, k, 1, 1, 1, 1, valid. The kernel K here is shaped for per channel convolution, for example, 2, 2, 2, 3, 2 multiplied by 2 size, 2 input channels, 3 kernel sets per channel. The output will have input channels multiplied by kernel sets, channels. This is how depthwise convolution reduces computation while keeping features. Finally, let's summarize the 3 key characteristics of convolution that make CNNs great for images. Sparse connectivity, each output pixel only connects to a small part of the input the kernel's size. This reduces computational complexity, fewer multiplications, and lowers overfitting. Fewer connections mean less chance to memorize noise. Parameter sharing, the same convolution kernel is used across the entire input. For example, a edge-detecting kernel is used everywhere in the image. We don't need a new kernel for every position. This drastically reduces the number of parameters. Shift invariance, if a feature, like a cat's ear, is learned at one position in the image, the model can recognize it anywhere else. For example, a cat's ear on the left is the same as one on the right. This makes CNNs efficient at processing images with objects in different positions. These three features work together to make CNNs powerful and efficient for computer vision tasks.